Okay, so,
It's not my day, is it?
oh, did it break?
Yeah, I think so.
Oh, no, those are tough. You can drop those off a building.
Thank you.
Don't drop it off the building. You can't really drop it.
What's my weekend plans for?
Okay, so for next week, okay,
Oh, you know, had the case on, right. Oh, that's disgusting. Okay.
all right, so for next week, October 5th is your unit exam, okay, and remember that on the unit exam, you're going to be asked to do basically all the things you've been asked to do thus far, okay, stuff with graphing, vector addition, acceleration problems, all that kind of stuff, okay. I will talk more in detail about the exam on Friday, okay, when we do our actual in-class unit exam review, okay, but I have already posted the review package. The only thing you really can't do in that review package is projectile motion, and we're starting that today, okay, so that's why I posted it. You can start having a look at that if you want to. Okay, and I also posted a key for it so you can check and see if you're doing it right. Please note that at the end of it there are some challenge problems. I would never give you anything like those challenge problems on the unit exam. They're just if you're starting to get really cocky and you need to be humbled a little bit, okay, you can do those ones and you'll feel humbled. And if you don't, well, good for you. I mean, if you don't feel humbled when you do them, you just get them right on, okay? All right, so for projectile motion, very simply, any object that is in unpowered flight in the Earth's gravitational field is a projectile. Okay, so basically any falling object, right? And that includes if I throw something up in the air, straight up in the air, that's still a falling object, even if it's moving upwards. It's still falling because it's accelerating at negative 9.81 meters per second squared. Any object in unpowered flight is a projectile. So, a missile is not a projectile because it's got a motor. A plane is not a projectile. It's in powered flight. Okay, so anything with a motor cannot be a projectile. Okay, by definition, because it's in powered flight. Okay, all projectiles basically do the same thing. They return to Earth. Right? Eventually. Now, there will be one exception to that when we get to Unit 3 and we start talking about satellites that orbit the Earth. Satellites that orbit the Earth are actually technically projectiles. They just never get any closer to the Earth, but they're always falling. Strange, but true. Okay, we'll talk more about that in Unit 3. Okay, so today, what we're going to look at is kind of the basics of projectile motion and kind of look at the first two types, and then we'll get to arced projectile motion probably tomorrow. Okay, so like we said, key points here, a projectile is any object in unpowered flight in the Earth's gravitational field. This usually has two dimensions to its motion, a horizontal and a vertical. All right, now, the only one that would not have two dimensions would be if you threw something vertically into the air. If you threw it straight up in the air, it obviously would have no horizontal component. Okay? What if I throw something horizontally? Would it have a vertical component? Yes, because the moment it leaves my hand, what is it doing? Falling. Even if I throw it horizontally. And that's one of the types of projectiles we're going to look at today is horizontally projected projectiles. The vertical dimension of any projectile motion is accelerated motion. It's affected by gravity, so the vertical part of it is always going to be an accelerated motion, okay, where you're going to use acceleration formulas to do your calculations. The horizontal dimension is going to be something that moves at a constant speed, because for us, we are not going to include air resistance as a factor in our projectile motion because it becomes quite a bit more complex to factor in varying wind speeds and all of that kind of stuff. Okay, so we just imagine that our projectiles fly in the perfect utopian physical world where there's no air resistance. That's simple. Okay. All right. So the essence of a projectile is this: what goes up must come down. Okay, gravity is always going to bring things back to Earth. Okay, gravity pulls the object towards the Earth while it travels horizontally and vertically. Okay, this means that an object fired horizontally will have the same flight time as an object that is dropped. Now, people really have a hard time wrapping their head around that. Here's what I'm saying. If I have a bullet and I'm holding it in my hand, and I have a gun right beside it with a bullet in it, and I pull the trigger and drop the bullet at the same time, they will hit the ground at the same time. Not in the same place, but at the same time. Because they both have to fall the same distance to the ground. And they're both going to accelerate towards the ground at the same rate. Okay? But people really have a hard time getting their head around that because they picture this other bullet flying really fast. And it is, but it's also falling at 9.81 meters per second squared. Okay? Mythbusters actually did a thing on this one time where they tested it and proved it to be true. Okay? That those two bullets hit the ground at the same time. Right? So this is something we have to take into account if we're trying to hit a target with any type of projectile, bow and arrow, gun, throwing a ball at a target, anything. Okay? We have to account for the fact that the ball, or bullet, or arrow, is going to drop as it flies, and we have to account for that. Okay? So if you have a gun, that's my best drawing, I saved it. This is my best drawing. That's sad, but true. Okay, so if I'm just firing a rifle, okay, the bullet will do this. Okay? It will arc down towards the ground, because that's what all projectiles do. Okay? If I had a bullet right here and I dropped it, it would do this. It would fall straight to the ground. And those two things would hit the ground at the same time. So if I'm trying to hit a target, I have to account for the fact that the bullet will drop as it flies. So I have to aim up, higher. Okay? I have to aim above my target in order to hit it. The longer the flight time, the higher I have to aim because the more the bullet is going to drop. The faster it's going to drop. So when you hear about these snipers who are hitting targets that are miles away, okay, these guys have their rifles, so they're not even pointed anywhere near their target. They're pointed way above it because the bullet is going to do this as it flies towards the target. Okay, it's going to arc through the air before hitting their target. Okay, it's crazy, but it's true. So that Canadian sniper who holds the record for the longest kill shot at almost 4 kilometers, scary thought, okay, 4 kilometers away, okay, would have had to aim so far above his target that it wouldn't even be funny, okay, to imagine how far above. So how do they do that? Scopes are adjustable. Right? How many people have seen the movie Saving Private Ryan? Okay, so somebody, if you haven't, it's pretty violent and realistic, but it's good. In that movie, Vin Diesel gets shot, spoiler alert. Okay? He gets shot by an enemy sniper, so their sniper is trying to hit the enemy sniper. And when he is sighting him in, he talks about what he's doing with the scope of his rifle. He says he's about 800 yards away, and that's 2 clicks. And most people hear that and they go, 800 yards is not 2 kilometers. That doesn't make any sense. But they don't notice that after that, he clicks his scope twice. And all that does is point the scope downwards to account for the flight time of the bullet and the amount of drop. Okay? So now, to get his target in his sights, the barrel of the rifle has to be aimed above the target. Okay? So he can still see the target in his sights, but the barrel isn't pointed at it. It's pointed way above it. Okay? And so that accounts for the drop. Okay? Does that sort of make sense? Okay? So all projectiles have to be done that way. If you've ever shot, it's much easier to see that and visualize it with a bow and arrow because it doesn't fly as far or as fast. And you can actually see the arrow do this. When you were a kid and you were playing with the hose in the backyard, right? If you had it on full blast but you still couldn't hit your brother or sister, you point it up a little bit and the spray would go further. Same idea. Okay? Angling it up will give it increased flight distance and increased flight time. Right? Okay. Is that sort of making sense? All right. So we're going to look at the simplest type of projectile. The simplest type of projectile is just a dropped object. Okay? If we drop something, okay, it's going to accelerate downwards at 9.81 meters per second squared until it hits the ground. Now, in the real world, of course, things don't fall at 9.81 meters per second squared the entire time. They eventually hit what? Not the ground. Yeah, terminal velocity, right? They hit this point where air resistance pushing up is equal to gravity pulling down. And when those two things equal, they actually fall at a constant velocity after that. Okay? Now, most people have this idea that falling objects are very fast, and they're right about that idea. Back in the late 90s, Lexus played on this for one of their advertisements, and they set up this ad. I'm going to show it to you in a minute. Okay? They took two identical Lexus, one of them on an airport runway, and the other suspended from a helicopter. And they were talking about how fast and powerful their new sports sedan was, and that it was faster than gravity. And so they were going to race the car on the ground and the car in the helicopter. They were going to drop the car from the helicopter and race to the point of impact with the car on the ground. And of course, when people start thinking about it, they're like, holy crap, that car must be really fast because it's outrunning gravity, but it's doing it on the ground. That's really impressive. Except, is there a way to set that up so the car on the ground will always win? Yeah. The longer that car is dropped from, or the higher it's dropped from, the longer it will take to fall. And you know that halfway down, or even less than halfway down, it's going to stop accelerating, and it's going to fall at terminal velocity, which you can go faster than on the ground. Okay? A car falling from an aircraft, especially if it's rigged, which it was, okay, falling flat has a very low terminal velocity because that's not a very aerodynamic dimension. If the car had done this and nosed down, no car on the ground would have ever beat it. Okay? But the car on the ground gets to drive in its most aerodynamic dimension and continue to use its engine to accelerate all the way to that point, whereas the falling object doesn't. It eventually hits a constant velocity, which it continues to fall at. Most people don't realize that, see this ad and go, I gotta go buy that. It's so fast, I gotta have it, okay? And so it impressed a lot of people. So I'm gonna show you the ad. The ad's impressive. Look, it looks really impressive. They did a good job of it, okay? But you really have to look at things critically to make sure you're not being played, because that's all advertising is trying to do, is play you and trick you into buying stuff that you probably don't need. So you can see, like, it looks really impressive. It obviously was not filmed at the same time. I mean, they would never have had somebody racing a falling car, okay, to that point. Plus, to get that car to fall perfectly straight down would be nearly impossible, okay? And so getting it to hit that target, they probably had to wreck 2 or 3 cars just to get that shot the way they wanted it. Okay? But obviously the car on the ground wins. Not only did it have a running start, okay, but it continues to accelerate the entire way to the X. It had, I mean, the falling car really has no chance, and you can set it up so that that car will always get there first. Okay? Now, a bunch of people sent that in to Mythbusters, and they're like, "Look, you gotta prove this can't happen. Like this, it's so impressive, but it can't be real." So Mythbusters did do a thing where they busted it. Okay, okay, so that's just straight falling. Okay, now what we want to look at are horizontally projected projectiles. Okay, so something that's projected horizontally has both a horizontal component and a vertical component. Okay, the vertical component is still accelerating at 9.81 meters per second squared. The horizontal component is going to be something traveling at a constant velocity. So V equals d over t will be the formula we use for that part of the motion. All right, so with a horizontal projection, okay? So let's say, like in Hollywood movies, they're always, for some reason, driving cars off cliffs, okay? And what does the car always do when it drives off the cliff? Right, and if you watch it in slow motion, because most of those effects are practical, they actually do drive the car off the cliff, okay? You see the object do this, okay? The motion becomes almost totally vertical very quickly. It's never totally vertical, but remember, this thing is traveling at a constant velocity horizontally. So its constant velocity, no matter how high it is not going to get any bigger. But its vertical velocity is going to get bigger all the way to the ground. Okay, which is why it starts to look like it's no longer going forwards and it's just all nosing to the ground. Okay, and that's because that part of the motion, the vertical part, becomes very dominant. Okay, so if I had a car, okay, I can't draw, that's my car. Okay, drives off a cliff, okay, at let's say 25 meters per second. Okay, what are some things that I could write down as givens for my vertical and horizontal components?
Well, that's called gravitational force and gravitational.
right. Okay, so vertically I could say this thing is accelerating at 9.81 meters per second squared down. Okay, what else do I know? Another number up there. That number is my horizontal velocity, the number that's not going to change. Okay? This car is going to continue to go horizontally at 25 meters per second all the way to the ground, just like the boat questions we were working on before. Even though I'm rowing across the stream, I'm also still going down the stream at the same time. Okay? So horizontally speaking, okay, the speed is 25 meters per second. All right, let me give you one more piece of information here. Let's say that this cliff is 100 meters tall. Okay, so there's two more givens. That one I just wrote there, and one more, and they're both vertical. So obviously the 100 meters is going to be this. But I have one more piece of vertical information, and it's not necessarily intuitive. When I drive off the cliff, how fast am I going vertically at time 0? 0, right? I drive off this cliff horizontally. So I'm not moving vertically the instant I leave the cliff. So my initial vertical velocity is 0. Okay, that is important. That's the thing people forget about horizontally projected projectiles, that their initial vertical velocity is 0. Okay? People have a hard time getting their head around that because they see this number. Okay? Remember, this is horizontal. That's the speed I drive off at. Okay? It has no vertical component whatsoever. All right, if I was given a question like this, with these givens, the question would probably ask me to calculate how far from the base of the cliff the car will crash. So what is it asking me to find? Is that a vertical or a horizontal number? It's a horizontal displacement. Okay, it's asking me to find this, okay, and this is horizontal. Okay? Yes, I have to travel vertically to get there, but I'm still traveling. I can measure that horizontally from the base of the cliff to wherever the car crashes. Okay? Now, if the horizontal part is governed by this, because it's moving at a constant velocity, in order to get D, I need to have T. Would it be true if I said this thing is moving horizontally for as long as it's falling? Yes, because once the car crashes into the ground, it isn't doing either one of those anymore. Okay? So the time in all projectile motion problems is the same for both the horizontal and the vertical part, just like it was in your boat questions. Okay? I'm moving downstream as long as I'm going across, because once I get to the other side, I'm not doing either one anymore. Okay? So could I find the time using my vertical information? I could, okay? Because I have a formula that has all of these things in it. I can find time using that formula. Because what's VI? 0. Okay, since VI is 0, okay, D really just equals 1/2 AT squared, right? So if I want to get T by itself, I'll divide both sides by 1/2 of A and square root. Okay, so now the time will equal the square root of 100 meters divided by 1/2 of 9.81. Okay, I could make both of those negative or not. Either way, it'll work out the same. Okay, so this thing is going to fall for 4.5 seconds. That is a long time to fall. 100 meters is a long way to fall. Okay, a lot of time to think about it. Okay, 4.5 seconds. All right, so now that I know the time is 4.51 seconds, I can now go over here and figure out how far from the base of the cliff the car is going to crash. Okay, so if I'm looking at that, D will equal V times T. Take my 25, multiply by 4.51. This thing is going to travel 100, well, I guess we only have 2 significant digits there. So 1.1 times 10 to the 2 meters. So over 100 meters from the base of the cliff is where that car is going to crash. That's like halfway up to C. Okay, it's off a big cliff. So a long, long way. Everybody following what we did there? All projectile motion questions effectively work like this. Okay, you have a vertical component where you're going to use acceleration formulas. You're going to have a horizontal component where you're going to use V equals D over T. Okay, those are the only 2 formulas you're going to use. Right? When we get to arced questions or angled questions, then you're going to have defined the 2 components, horizontal and vertical, in order to get VI and V. Okay, so you got to find vector components to get those. When we get to those, we're not there yet. Right? Everybody okay with that? Okay. Then let's have a look at kind of what this looks like. Only projected a projectile here. So let's have a look at. Okay. Try this one. On the last one, I gave you the height of the cliff. This time they're telling you you want to calculate the height of the cliff, and they're giving you slightly different information. So we want to figure out how high a cliff has to be so that a person who runs off the cliff at 8 meters per second, okay, would hit the water 15 meters from the base of the cliff. Right? So I'll give you a few minutes to kind of get it drawn out and figure out what your givens are, and then we'll have a look at it. So our givens should look something like this. Okay? We have a person inexplicably running off a cliff. Okay? And they're doing so at 8 meters per second. We want to know the height of the cliff if they're going to encounter the ground 15 meters from the base of the cliff. Okay? That's what we're told. So, horizontally speaking, I'm given 2 things. What am I given? Distance and velocity. Okay, I'm told that they're running at 8 meters per second and they're going to travel 15 meters. Okay, that's what the question gave me. Horizontal distance is always the distance from the base of the cliff. What did they give me vertically? Seems like nothing, but they did give me 2 things.
Initial velocity.
Right, what is the initial velocity?
0.
0. It says they ran horizontally off the cliff. If they ran horizontally off the cliff, they have no vertical velocity. Okay? It doesn't say they ran to the edge of the cliff and then jumped upwards. Okay? It doesn't say that. It says they just ran right off. Right? That means they had no vertical component to their velocity when they left. And the other thing we know is that obviously it has to accelerate at 9.81 meters per second squared. It wants to know the height of the cliff. So it wants to know this, which would be my vertical displacement. Okay. What do I need if I want to find D? That I could maybe find using my horizontal stuff. Time. Yeah, I can find time with my horizontal information. Remember, horizontal is always V equals D over T. Okay? If that's the case, then I can find T, because I've got 2 out of the 3 parts of that formula. So T equals D over V, right? So that'll be 15 over 8. All right, we're looking at 1.875 seconds. Just like the boat questions, bless you, I'm falling and moving horizontally at the same time for the same amount of time. Right? So I can move time over here, okay, and say it's 1.875 seconds. All right, now that I have that, now I can use this formula. D equals VI times T plus 1/2 AT squared. VI is 0, so really I'm just plugging into 1/2 AT squared. And when I do that, I'm going to get that the height of the cliff is 17 meters. Okay, everybody follow me there? The only other way that question can be asked is to ask you to calculate the speed they ran off the cliff at. Okay, in which case they would have to give you the height of the cliff and the distance from the base of the cliff. They would give you those two things and you'd be able to calculate it from there. Okay, it's all basically the same. You're going to use an acceleration formula and you're going to use v equals d over t for any object running, falling, flying, running, jumping, whatever off a cliff. Okay, or a diving board or whatever. All right, questions on that so far? Okay. So there's the other kind that I just mentioned. Okay, so a ball rolls off a 1.2 meter high table, hits the floor 0.85 meters from the base. What speed did it roll off at? Okay, give me a few minutes to try that. So we have a table that's 1.2 meters high. Okay, it hits the floor, this ball that rolls off of it, okay, 0.85 meters from the base of the table. Okay, we're looking for the speed the ball rolled off at. Okay, so we don't know what that is. Okay, but we do know the vertical initial velocity is 0 because it rolled horizontally, right? Okay, we also know the acceleration is 9.81 meters per second squared, and we know one other thing. Distance, yeah, the height of the table is the vertical distance. Okay, 1.2 meters. All right, horizontally speaking, I only know one thing right now, and that's the distance, or displacement. Horizontally is 0.85 meters, that's all I know. They want me to find the horizontal speed. So, what do I still need? We're going to find v using v equals d over t. What do I need? I need time. Can I find it with my vertical information? Okay, this is how all projectile motion questions are going to work, guys. You know what you're looking for. Can I get what I need to get that from the other component? Okay, so if you're looking for something in the horizontal, you're going to need to calculate one more thing from what you're given in the vertical part. And more often than not, it's time. Because time is the one thing that counts for both of them. Okay, so I'm going to use this formula, t equals vi times t plus 1/2 at squared to solve for time, knowing that vi is 0. Okay, so time will equal the square root of d over half of a. Okay, so time will be the square root of 1.2 divided by 1/2 times 9.81. All right, so we're looking at 0.49 seconds as our falling time. All right, so v equals d over t, 0.85 divided by 0.49, okay, and that'll get us our overall horizontal velocity. So. All right, so it rolled off the table at 1.7 meters per second. All right, so all these horizontal ones work the same. There's only going to be 3 things you'd be asked for with a horizontal projected projectile, and that is horizontal speed, vertical distance, or horizontal distance. Okay, you're always going to have to calculate time, okay, in order to calculate any one of those things. So we're going to just kind of introduce the projected at an angle type of questions today. We probably won't get into much of how to solve them, but we're going to look at kind of how they work. Right? So if I have an object and I throw it into the air at an angle, what is it going to do? Yeah, it's going to start falling. As soon as it leaves my hand, it's going to fall, but that falling is going to look like this. Okay, it's going to travel in an arc, a projectile arc. Okay, if you've ever thrown a ball, played golf, okay, or anything that would involve making something go, okay, you've seen this projectile arc. You can best see it with water. Okay, if you've got a hose running and you squeeze the hose, it'll always make that projectile arc. Everything does that on Earth because gravity is pulling it back. Okay, the only reason you see the arc, the whole arc, okay, with these is because they start moving which way? Upwards. Okay, this object here, let's say it was thrown at 20 meters per second, 30 degrees above the horizontal. I'm just going to adjust where I drew this line. Okay, if I throw it at 20 meters per second, 30 degrees above the horizontal, it's moving somewhat horizontally and somewhat vertically, right? If it's at an angle, it's got a vertical component and a horizontal component. Over the last couple of weeks, we've been looking at how to calculate x and y for any angled vector. Okay? What we're looking at here is that from a projectile motion perspective. Okay? So on this, y represents the initial vertical velocity. It's how fast it was moving upwards the moment it was fired, thrown, released, whatever. Okay? And x represents the horizontal velocity. How fast it's moving straight across at the moment it's released. Okay? The difference between these two things is this one is going to be constant, it's not going to change, and this is going to change because it's undergoing accelerated motion. Okay? So it doesn't matter whether I have an angled projectile or a horizontal projectile, the vertical part is always accelerated motion, the horizontal part is always constant motion. Okay, so with just that much information, a question would probably ask you something like this. How far horizontally will this object travel? Okay, that's what it could ask. Now, just looking at this, you're probably thinking, how am I supposed to figure out horizontal D with one number? Well, if I know this number in the angle, so actually two numbers, okay, I can find its y component, which will represent this. I can find its x component, which will represent this, and I actually do have a few more numbers. I would also know what vertically. I'd also know that. Here's the other thing I know. I'm not actually going to solve this because I don't want to really get into that today. Okay, but here's the other thing I would know. If the launch point and the landing point are level, VI and VF are what? Equal. Okay, think about this. If I throw this thing straight up in the air, when it comes back down to my hands, it has done the exact opposite of what it did going up. When it left my hand, it was slowing down, slowing down, slowing down at 9.81 meters per second squared. And when it got to the top, it reached a speed of 0. And then it fell the exact same distance back down at the exact same rate of acceleration back to the same place. Which means it has to have gone right back to here and end up going the same speed it was thrown at. Okay, everybody kind of follow me on that? Okay, now that's in the perfect physical world. Right? In the real world, it never comes back at the same speed because eventually everything starts to what? Okay, just look at what the pen does. Okay, if I throw this thing far enough, even if I throw it straight up in the air, on its way back down, it's going to do this, and it's going to tumble. When it tumbles, will it fall as fast? No. Okay, it's the reason why if you fire a gun up in the air, you don't really have to worry about the bullet coming back down. Okay, the bullet's going to tumble on its way back down, so it's not like if you did this, you'd have to worry about dying. Okay, first off, the bullet would never fall perfectly straight back down. Have any chance of hitting you. Okay, and even if it did, it would be going very, very slow when it came back down because it's going to tumble. All right, everybody with me there? All right, so those are some of the kind of principles behind a angled projectile or angled launch of a projectile. So this is what we were talking about with if you're trying to hit a target a long ways away, even if it's as simple as you're throwing a touchdown pass in football, okay? If you're trying to hit that target, you don't throw it horizontally, okay? Nobody throws a pass that's on a perfect rope, okay? It's perfectly horizontal. Nobody can throw that fast, okay? It would be impossible, right? You have to arc it, okay? And make it come back down, right? Same with like a kickoff, or if you're punting, right? It follows that projectile arc, okay? All the way to the target. And you have to, the higher up you can make it go, the farther it will go until you get to what angle? 45, yeah, okay. 45 degrees is the maximum angle arc before, so if this was a hose, and I'm shooting the hose, okay, and I'm going angling, it's gonna go farther, and then when I get to 45 degrees and I keep going, it's gonna start coming back. Yeah, I mean, if I keep going and get back to vertical, I'm gonna get wet. Okay, it's going to go straight up, come straight back down. All right, so at 45 degrees is where you'll get your maximum distance. Okay? And so if people are firing like cannons, you know, or artillery or things like that, where they're firing a projectile several kilometers, okay, they have to really know the speed it's being fired at. They have to know the distance it's going to travel, so they can put the right amount of powder in the gun and have it at the right angle and all of that kind of stuff. There's actually quite a bit that goes into it, okay, to be accurate. All right, so I'll show you an example here. Okay, so he made a giant slip and slide that goes down a hill like this. And then he built a ramp. Like this. Okay? So he's gonna slide down the slip and slide, and he's gonna shoot off the ramp at an angle. He's gonna become a projectile. Okay? And he's gonna land in this little kiddie pool. Okay, you know the blue inflatable ones? You know, they're like this deep, okay? Like 2.5, 3 feet deep. Okay? He's going to land in that little kiddie pool and somehow not die, even if he hits the kiddie pool, which is like crazy that he would actually do that, right? Because he's going to fly like a seemingly impossible distance through the air and land in this kiddie pool. It's crazy. Okay, so this video came out and it went like absolutely viral because everyone was like, "Ah, it's so amazing! How do I build one?" Right? Because there's crazy people out there that would do stuff like that. Okay. But yeah, see, there's crazy people. So, so he builds this thing and he flies off. He lands in the kiddie pool. Now, I mean, the distance he's flown would require him to be going very, very fast, and to land in that volume of water, even if he was able to hit the target, would not be enough to save him from serious injury. Yes, yes, it was a hoax. Okay, they actually did it with CG, but they did a good job of it. It looks fairly real. Okay, all they did was, you know, have the, you know, he kind of went partway down the ramp, and then they just kind of cut it, CG'd the rest, and then they filmed the part where he was already in the pool, and he just shakes the pool to make it look like there was a splash, and then gets up like he was flew all the way.
Tested it, like put like not a human, but like something else to make sure you get the pool?
I'm so glad you asked that. I'm sure they didn't, because this was all just a hoax to get YouTube money. But
Why the hell would you do that?
well, they made a lot of money,
Yeah.
so that I would guess that would be why. That would be my motivation. Okay? As long as I wouldn't be, as long as I'm not going to be held legally liable for anyone who tries the damn thing, like, yeah, that would be my thing. But MythBusters, of course, got sent this, and everyone's like, "Come on, you gotta tell that that's fake." So they did. They did it.
With a real person?
With a real person. With Adam and Jamie. They did this. Okay? Into a lake, not into a kiddie pool. Okay? But we're gonna watch that and show kind of how it works.